Hi everyone, welcome to the conformational analysis of n-butane. Before moving on to detail about the conformational analysis of n-butane, I just would like to brief about why we need to talk about conformational analysis. Molecules are not rigid objects. Bonds can rotate, like where you see here, bonds can rotate freely, producing different spatial arrangements of atoms, like cis, trans, anti, uh, gauche, fully eclipsed, partially eclipsed, etc. Atoms called conformations. Conformational analysis of n-butane is a cornerstone concept for organic chemists as it establishes the foundational principles of steric strain, torsional strain, and non-bonded interactions that govern molecular shape. Understanding how butane's energy landscape shifts with the bond rotation equips chemists to predict the preferred three-dimensional geometry of far more complex molecules, from drug candidates to natural products. The anti versus gauche energy difference is directly informs the design of stereoselective reactions. That's very crucial, where controlling which conformation a substrate adopts determine the outcome of a bond formation. In synthesis, recognizing that transition states often mimic low energy conformations as formalized in models like Filkin and Zimmermann-Traxler, allows chemists to rationalize and predict diastereoselectivity. Ultimately, butane serves as the simplest model for understanding conformational control, a principle that underpins everything from enzyme substrate recognition to the design of chiral catalyst. Conformational analysis study of the different spatial arrangements of atoms produced due to rotation around a single bond. N-butane is one of the simplest molecules used to understand conformational analysis because rotation around its CC, this CC bond produces several important conformations. It is an excellent model molecule for studying bond rotation, particularly bond rotation, molecular stability, steric strain, and torsional strain. And before we move on to the n-butane conformational analysis, we must know uh, introduction to n-butane conformational analysis. In n-butane, rotation occurs around the central carbon-carbon bond between the two middle carbon atoms, that is C2 and C3. Because of this rotation, n-butane can exist in several conformations such as eclipsed, gauche, partially eclipsed conformation, and anti-conformation. These are the four different conformations one can obtain by rotating the C2 C3 single bond of the n-butane. That would give us the better results when we work on the different chemical reactions. The outcome can be effectively predicted. These conformations have different energies and stabilities. Why is the conformational analysis important? Conformational analysis helps us to understand the following. One is molecular stability, energy differences between conformations, reactivity of the molecules, and shape and behavior of organic compounds, and also biological activity and stereochemistry. It is very important in organic chemistry because molecules are not rigid, as we have mentioned earlier. They continuously rotate and change shape. And when we come to the n-butane conformational analysis, there are two important factors one has to consider. One is the role of torsional strain. What is torsional strain? Torsional strain arises when bonds on adjacent uh, carbon atoms eclipse each other, where the electronic cloud that would repel each other in eclipse conformations, particularly when we discuss later the later part of our talk, the electrons clouds of CH bonds repel each other. Due to that, you get the torsional strain. This increases the energy. Therefore, eclipsed forms are less stable and staggered forms are more stable. That also we will discuss why it's so. And then the next one is the role of steric strain. After the torsional strain, what about steric strain? Steric strain occurs due to repulsion between large groups that come too close to each other. In n-butane, the two methyl groups may come close during rotation. This causes steric repulsion, especially in the fully eclipsed conformation. The CH3 repulsion is maximum. When we move on to the uh, latest slides, we will be able to see how these two methyl groups, in fact, uh, having the more repulsion, therefore destabilizing the molecule because of the energy becomes very high. As you can see here in this diagram, energy level diagram, the stability of n-butane conformations decreases as steric and torsional strains increase during rotation about the CC bond. Let us discuss in detail using the energy level diagram of n-butane. What you see here, it is a energy level diagram for n-butane. So highest energy for particular conformation, that is nothing but eclipsed, and then it's coming down to another conformation, subsequently increasing, and again it's coming to lowest level. It's a more stable conformation, and similarly one can anticipate going up and down and going up. So this will be discussed in detail in the next slide. The stability order also, one can see that anti is a greater stability compared to gauche, and gauche is having a greater stability compared to eclipsed, partially eclipsed. Finally, the lowest least stable one is the fully eclipsed. How does it vary? How one can rotate the uh, bond between C2 and C3, how these steric and torsional strain play a major role in order to predict the stability of the molecule and their energy. Now let's discuss in detail about the n-butane conformations, different conformers. The stability of n-butane conformations is governed by how steric and torsional strain build up as the molecule rotates around its central CC bond. As the strains increase, the potential energy rises and the stability drops, and the energy diagram of n-butane makes this relationship very clear, where we can see the n-butane energy level diagram, conformation energy level diagram, x-axis diagonal angle, y-axis energy. The first conformer is the fully eclipsed, where you can talk about the starting point is fully eclipsed conformation, zero diagonal angle. This is a zero diagonal angle, and if you see the energy for this particular conformer is the maximum, because at your diagonal angle 0, the two methyl groups directly eclipse each other. This is the worst case scenario. Maximum steric strain from the two bulky groups clashing, compounded by full torsional strain from all eclipsed bonds. We all know what is torsional strain, arising from the electron cloud, in fact, present in each bond, because they are on the same side. They have maximum repulsion, therefore, that would destabilize the conformer. And also the steric reasons, the two methyl groups are very close. Even the steric strain is maximum in this particular conformer, right? So therefore, if you look into that, the energy is the maximum. And next, when you rotate 60 degree of this particular conformer, the diagonal angle 60, when it comes to 60 degree, where you can anticipate it forms the gauche itself, one of the staggered conformer, where you can see that energy is dropping to 0.9 kilocalorie from 4.5 kilocalorie. This energy minimum resulting from the less steric strain as well as torsional strain. However, when you rotate another 60 degree, that is 120 degree diagonal angle between these two bulky methyl groups, again it's becoming partially eclipsed. And when compared to gauche, this partially eclipsed will have slightly higher energy, at the same time lower compared to the fully eclipsed. That's what you see here. It gives 3.6 kilocalorie when compared to the gouache, right? So this is because of the, what you can say, eclipsed at 120. One methyl group eclipses the hydrogen on the adjacent carbon. Torsional strain from eclipsing bond combines with the moderate steric strain, producing a local energy maximum. The molecule passes through this state very quickly, and then when you do one more 60-degree rotation, that resulting into 180-degree diagonal angle, where you can see the two methyl groups are far away. Hence, that's opposite each other, maximum separated. Both steric and torsional strain are at their absolute minimum in this case. So therefore, if you look at the energy, right, energy is very, very less. You can say that it's coming to lowest energy for this particular conformer, that is the anti. Again, it's one of the staggered conformer, and all the antis are staggered, but otherwise not possible. When you move on to the next one, again the same thing is repeating when you move to another 60-degree, where 240 diagonal angle, again it's kind of partially eclipsed, same kind of scenario happens, and the energy is increasing. And another 60-degree, it results in the gauche conformer, that is the one can say 300-degree rotation. And finally fully eclipsed you reach when you do one more 60-degree rotation, that resulting in the anti-conformations. So therefore, if you carefully look into that, based on the energy, how these conformers having the stability based on uh, steric as well as torsional strain. The key takeaway is the remains the same. Stability and strain are inversely related throughout the rotation. Every eclipsed arrangement spikes the energy. Every staggered arrangement lowers it. That's what we have seen, because the methyl groups are far away. Hence, the steric strain is getting decreased as well as torsional strain. The anti-conformation at 180-degree diagonal angle wins because it eliminates both steric and torsional strain simultaneously. Yeah, thank you. Having discussed in detail, now let's summarize what we have learned so far about the conformational stability in n-butane. Normally it depends on two parameters. One is the steric and the torsional strain. The higher steric that's a strain increases potential energy and decreases stability during rotation about the central carbon-carbon bond, that is C2 and C3 in the case of n-butane. And we have different rotations, like at 0 degree. If you carefully look into that fully eclipsed conformation, the two methyl group, if you look at the blue and red, directly eclipse each other, causing maximum steric and torsional strain. Both strains are high in this case. So this is the highest energy and the least stable conformation, as you have seen earlier. This particular conformer clearly depicts it. And when you do the 60-degree rotation, you can see that the methyl group is slightly away, that is a 60-degree away, that is a gauche conformation. The methyl groups are staggered, but still uh, they are close enough to experience slight steric repulsion. Therefore, giving a local energy minimum with a moderate stability, and when compared to 0 degree, that is a fully eclipsed conformation. However, when you further rotate the methyl to 120-degree, where you can see 120-degree, that is nothing but partially eclipsed conformation you would obtain, and yeah, methyl group eclipses a hydrogen atom, so therefore that would result in both torsional and moderate steric strain, and producing a local energy maximum. in the case of 120-degree rotation. Finally, when you look at this, at 180-degree anti-conformation, the methyl groups are farthest apart. If you look into that blue and the methyl red color, farthest apart, the methyl groups are farthest, minimizing both steric and torsional strain. This is the lowest energy and most stable conformation. And further rotation repeats the same pattern symmetrically from 240 to 360 degree. Hence, one can say that that would repeat from 0 to 180 degree. Yeah, thank you.